So in the previous part, I talked about what the linear ODE looks like, what's a homogeneous ODE. So let's talk about this specific type of linear equations that are both linear and homogeneous. So the ones that can be written in the form L of y equals 0, and as an example that I'm going to work with right now, let's say you have y double prime minus 4y equals 0. We're going to learn how to solve this later on, but let's focus on the aspect of linearity and homogeneity and what this has to do with how we develop solutions or differential equations. So I already wrote this important remark. Let's go over it a little bit. So this, we're not going to prove it, but we're going to take it for granted, although those of you who take a little bit of linear algebra, and you have taken linear algebra or you are taking it right now, at the same time when you take differential equations. So you're going to learn about what a vector space looks like, but what that means in our case is that essentially the solution, the general solution, can be written as a linear combination of independent solutions. So if the ODE is again linear and homogeneous, it is a fact proved in math, in the mathematical theory behind these differential equations, that the solutions, so the solutions of any linear and homogeneous ODE form a vector space. It means that you can write the general solution as a linear combination of independent solutions. To be more precise, you need n independent solutions if the ODE is of order n. So that is the main result, and what probably the most important result related to differential equations, to the linear ODEs, namely that if the equation is also homogeneous, you know already a lot about the structure of the general solution, namely that it can be described by a finite number of independent solutions. So once again, it's worthwhile to pause a little bit and maybe rewind to make sure you understand this fundamental concept. As long as your equation is linear and homogeneous, the general solution is simply a linear combination of as many independent solutions as the order of the ODE. So for example, because of this theorem, I know already that to describe the full solution of this equation, I need to produce two independent solutions. If the equation is of the first order, I need only one, and you kind of know this already. So for instance, if you go back to the exponential ODE, if you have y prime, let's say minus 5y equals 0, that's a linear, first order, homogeneous ODE. Now we know how to solve it because we managed to do this by separation of variables, if you remember. But notice that it fits this remark I was talking about. How many solutions do you need to describe this? Well, just one, because it's of order 1. So of course I know, because I memorized the solution of the exponential ODE, I know that y, the general solution, is some constant e to the 5t. So you could think of the general solution as a linear combination of 1. Okay, so just one independent solution is needed, and then a linear combination of 1 just means a constant times that solution. So this describes everything. On the other hand, in this second example, I will need two independent solutions. Again, we're going to learn pretty soon how we solve that. For now, take for granted that one independent solution is e to the 2t, and another independent solution is e to the minus 2t. If you don't believe me, we can actually check immediately. Notice that y1 double prime, well, y1 prime is 2e to the 2t, y1 double prime is 4e to the 2t, and when you plug in these guys, y1 double prime and y1 into the equation, so y1 double prime minus 4 y1 prime, that's 4e to the 2t minus 4, excuse me, this is just y1, minus 4 e to the 2t is 0. Okay, so it's not difficult to check that you get the same thing if you check y2 as the solution, right? In fact, let's just actually do this as a matter of an exercise. So y2 double prime is minus 2 e to the minus 2t. y2 double prime is minus 2 times minus 2 e to the minus 2t. That's 4 e to the minus 2t. And if we plug it in now into the ODE, y2 double prime minus 4y2. What does that become? Well, it's 4 e to the minus 2t minus 4 quantity y2, which is e to the minus 2t, and obviously this is 0 as expected. So again, take it for granted for now. We're going to learn how to find this, but notice that indeed y1 and y2 are the solutions of this ODE. So going back again to the remark I wrote here, once I have these two independent solutions, right, so they're not the multiple of each other, they're independent, then I know the general solution of this equation is just a linear combination of these two independent solutions, c1 e to the 2t plus c2 e to the minus 2t. So basically the whole course develops around this concept, right? I mean, if I have an ODE of order 2 or more, then I need to find 2 or more independent solutions to come up with a general solution of the linear homogeneous ODE. We're going to deal primarily with first or second order in this class. But for now, again, pause for a moment and make sure you understand this entire concept. How many independent solutions do I need to solve a homogeneous linear ODE? You're going to need as many independent solutions as the order of the ODE. So you're going to need 1 in the first order, you're going to need 2 in the second order. You may wonder why actually this homogeneity and linearity plays a role in this formula. Well, it has to do really with the fact that once you find 2 solutions of a linear ODE, any linear combination of them is also a solution. So for example, once I establish that y1 double prime minus 4y1 is 0, y2 double prime minus 4y2 is 0, it's not difficult to realize that if I plug in, instead of y, just a linear combination of y1 and y2, like that. Well, first of all, the fact that the equation is linear allows you to distribute the derivative. That is the key thing, right? How do I differentiate a sum? I differentiate each term of a sum. That's only true for a summation. Yeah, you cannot distribute the derivative over a product. So because the equation is linear, that allows me to distribute the derivative like that. And then, of course, to recombine the terms together by collecting the y's together. So for example, I can pull up c1, and then I can pull out c2 from the other 2 terms. And this will be 0 because we know already that y1 double prime minus 4y1 is 0. We know that y2 double prime minus 4y2 is 0. So c1 times 0 plus c2 times 0 equals 0. So obviously linear homogeneous means that any linear combination of 2 solutions is also a solution. It's important to point out why you need linearity, right? I mean this for so I can distribute the derivative, and why you need 0 on the right hand side, because otherwise this last statement won't be true if you don't have 0 on the right hand side. So that's why you need both linearity and homogeneity for this theorem to hold. So essentially at this point we have a general mean, roughly speaking, on how to solve linear ODEs that are also homogeneous. The next piece of the puzzle is how do we deal with a non-homogeneous equation. And you'll see that even in that case that's connected to the homogeneous part of the equation. So in the in the third part of the lecture, we're going to deal with stating a general theorem of solving linear ODEs which are not necessarily homogeneous. So we're going to have basically a main theorem that we will pursue for the rest of the class. Essentially that theorem will provide methods of implementing these ideas and actually finding the solutions in various cases. So hold on, and we'll get back with the third part pretty soon.